So in my previous video on spinors, I talked about relativistic spinors and we discussed them in depth, and I stopped at when I defined an invariant for relativistic spinors, right? So in this lecture, I'm going to move forward and we are going to talk about actions that are associated with relativistic fields and of course spinors, right? So you might stop me here and ask me why do we have to talk about action, right? Okay, so and I'll tell you that of the various formalisms that we have for describing mechanics, the Lagrangian and the associated action principle is the most useful for our purposes. Okay, you might be satisfied, or if you're not, you will stop me again and ask me why is that the case, right? So let me tell you that it can be actually generalized in several ways. That's why. And so say we have a non-relativistic case and we have to go or shift to a relativistic case. Relativistic. So what do we have to do? Well, before I talk about this, let me just quickly say that in general or classically you write your action as the time integral of your non-relativistic Lagrangian, right? So coming back to this, where I said that the action could be generalized in several ways. This all we have to do is change this time integral into a space-time integral. So it's d for x, right? And going from something that is point particle to fields. Now for this, what we do is we have for point particles some function of time, that is position function with respect to time, and we just change that with some field function, say phi of a 4 vector, that is x mu, right? So we have another one where you might be in classical mechanics and you have to go to quantum mechanics. What do you do in this case in terms of action, right? Well, to understand the physics of the situation, we go ahead and we say that the action has to be minimum, and so we say delta S, which is the change in action, is equal to 0. So we take the extremum value of the action, right? And to go to quantum mechanics, now here I'm going to talk in terms of the path integral, right? And so what that is you talk about this thing instead. So that is the total derivative of phi, that is your field, and times the exponential of iota over h bar times s. Now I talked about this thing in my video on frameworks for doing physics, and so there I might have talked about this thing in depth. I should not say depth, but I talked more about it in that video than in this video, right? Okay, so this is the reason, right, that we can generalize the action in several ways. Now again, you might stop me and ask me, is this only the reason? Well, no, of course not. What we can also do is we can work with symmetries in this case, and symmetries are actually very important in physics. So you might now again ask me why, right? But of course somewhere I have to stop, and so I'm going to stop over here. Now I have done a proper video on relativistic Lagrangian and the principle of least action associated with that. So I'm not going to essentially derive this relativistic Lagrangian from the action, but what I'll do, because I'm so kind, right? I'm going to quickly rush over the procedure, right? Or just quickly give you an overview of this. So say we are going to talk about now the action Lagrangian and the equation of motion for relativistic fields. For relativistic fields. It took me longer to write this than I'm going to talk about it. So okay, so well, what do we do, right? So we simply replace some of the quantities in recall that first of all we have first let me just say recall that we have our Lagrangian is a function of some generalized position, right? And some that the time derivative of this generalized position, right? So that's represented with q dot. Okay, so what we do is in if we are going to talk about relativistic fields, we simply replace q of t, this generalized position, with, or as a function of time, we replace this with some generalized field that is a function of this 4 vector, right? And well, we are done about this part. We still have this one. So what we do is we replace the derivative of generalized position with the obviously with the derivative of the generalized field with respect to this x mu, right? This 4 vector, right? And finally we have recall that we had this action was the time integral of the Lagrangian, so we have to replace this thing, and we simply go ahead and replace this time integral with a space-time integral that is d for x, right? Okay, and so with all of this replacing things here and there, we have action for relativistic fields, that is this thing. So Lagrangian is a function of this field phi and the covariant derivative of the field, right, with of course d for x, right? Okay, now well, here let me just stop and say that you might also ask over here that, well, we previously over here we said that we use this part when we have to talk about quantum mechanics, right? But what I'm going to do is I'm going to use this thing, that is, I'm going to stay in classical mechanics. You might say that I'm crazy, right? But no, I'm not. Because it turns out that classical equation of motion is actually going to be useful, despite the fact that we are talking about particle physics and these particles are indeed quantum particles. So why not talk about quantum mechanics directly? Well, as I just said, that it turns out that the classical equation of motion is actually going to be very useful for us, right? Okay, so moving on, we can now arrive at the equation of motion for relativistic fields, which I said that I'm not going to do an explicit derivation of. I was just kind enough to give you this much overview. But if you impose some boundary conditions and you solve with the setting this action, taking the extremum value of this action, you arrive at the relativistic equation of motion, or the relativistic Euler-Lagrange equation of motions, right? And so which is, let me just write it down over here, relativistic Euler-Lagrange equation of motion. Yeah, I am pretty lazy, right? Okay, so it is partial derivative of Lagrangian with respect to phi minus partial over partial x mu times partial derivative of Lagrangian over partial derivative times partial mu of phi, right? This thing is equal to 0, right? And this is then known as the relativistic Euler-Lagrange equation of motion. Okay, now if you are familiar with the Lagrangian mechanics, which you are if you're watching this video, then you are probably used to constructing the Lagrangian with kinetic and potential energy of the degrees of freedom according to this equation over here, that is L equals T minus V, where T, this thing, is your kinetic energy and V is your potential energy, right? The idea of this potential energy is useful, of course, but for our purposes, it is better to directly associate the potential energies with the interaction between things, right? Fields in our case, right? So interaction between the fields. So generically, you would expect to split the Lagrangian into two parts. That would be Lagrangian is the sum of the kinetic term, I don't know if I'm going to spell this right, but anyway, plus the interaction term, right? So interaction. I'm lazy, I'm just going to stop right there. Okay, now you might stop and ask, why did I use this positive sign over here, right? Why am I adding the two fields? Well, the reason is that this sign is not important as of yet, since we haven't specified on how do we construct this interaction Lagrangian. Okay, now that's out of the way. Now we have no interactions. If we have no interactions, in that case, we have what is called a free theory. A free theory. Okay, in a free theory, we have no interactions. Okay, And so if that's the case, then we have our free Lagrangian is equal to this kinetic Lagrangian. Yeah, this time I spelled it right, I guess, and here I could not. Anyway, so sometimes we actually call this kinetic term, this one, we call this the free Lagrangian, right? So whenever I refer to a free Lagrangian, I'm just talking about the kinetic term of our Lagrangian, right? Okay. Now, the program that we are going to follow is that first we will consider a free Lagrangians, right? And then we are going to introduce interactions through the principle of local gauge invariance, right? So we are going to talk firstly about free Lagrangians. And now finally coming to the topic of, or a very interesting topic of, free Lagrangians. Right. Okay. So in classical point particle physics, you would generally say that your free Lagrangian, which is, remember, it is the kinetic term, so it is just equal to T, which is equal to then P squared over 2m. And if you expand this further, what you get is your very famous formula for kinetic energy, that is half mv squared, right? But we have a problem here, right? In this Lagrangian, this bloody m, the mass, is going to be a problem for us when we are talking about relativistic fields, right? Not relativistic fields. Specifically, when we are going to talk about massless fields, right? So, say a photon field, the electromagnetic field, it's a massless field, right? Because photon is massless. Okay, so here I would also like to mention this, that whenever something has a mass, right? If there is a mass, no matter how small that is, that thing will always move slower than the speed of light. However, if anything that is massless, and trust me, there are things that are massless, a very classic example would be, of course, a photon, right? A photon is massless. So anything that is massless is always going to be moving at the speed of light, right? So yeah, dig this inside your brains. Right, now this thing is based on a massive scalar particle, and it is built from the 3 momentum or a 3 velocity, right? So it's built from 3 momentum. Now 3 momentum, of course, is just a momentum that has 3 components. Here we did not care about including time, right? Because we are not as smart as Einstein, right? We were not as smart as Einstein, right? Now of course, then all of this story has to change for massless relativistic fields, right? Now, fortunately for us, we only have 3 cases that we have to consider, right? So first one is spin 0 case, which is of the Higgs field. Then we have what is called a spin half field, which is going to be for the matter, right? So matter are spin half particles. And then finally we have the spin 1 fields, that is the force fields or force particles, right? So the carriers of force, that is Yeah, force particles, right? Okay, so now I have something to say here, right? That we are not going to derive these free Lagrangians. Of course, doing so, it can be done in various ways at different levels of sophistication. And to be brutally honest with you all, several of these Lagrangians were actually guessed in their original discovery, right? So what I'm going to do is I'll just present them one by one at a time, right? And then what we are going to do is what we will derive is then essentially that is the Euler-Lagrange equation of motion for each of these different spin cases, right? So of course we are going to have different Lagrangians for this one, and for this one, right? So we'll have 3 different Lagrangians. Right, now let's go ahead and talk about this free Lagrangian. So first case we'll consider is a spin 0 case, and spin zeros are also known as scalars, right? So these form a scalar field, that is phi. Right, now I'm just going to write down this Lagrangian that satisfies these spin 0 fields, that is equal to 1/2 partial mu phi times partial mu phi plus 1/2 mc over h bar whole squared times phi squared. Right, now carefully look at this Lagrangian. This Lagrangian is very helpful to us if we're going to talk about massless fields, right? And it is obvious if you see it now that the mass term is completely a separate term, right? So we have mass in this one and we do not have m in this one. So what the m is equal to 0 case, that is the massless case, can be then consistently handled by this Lagrangian, right? And so that's the beauty of this Lagrangian. Now if we can go ahead and actually write this Lagrangian as 1/2. I'm just going to play a bit with the indices with this metric tensor. Partial mu phi partial nu phi plus 1/2 mc squared, mc over h bar whole squared times phi squared, right? Now I did this for one particular reason, that I just said that we are going to derive the equation of motion for these Lagrangians. Now to do that, what we need is then the relativistic Euler-Lagrange equation of motion, that is partial L over partial phi minus partial over partial x mu times partial Lagrangian over partial mu phi is equal to 0. Right, now all you have to do is take this derivative of this Lagrangian that I have written over here, and then take this derivative of this, again the Lagrangian that I have written over there. So this would actually be a very good exercise for you to brush up on your mathematics skills, and if we go ahead and do that, then what we get is we get mc over h bar squared, right? All of these constants come out, and phi, again remember we have to take the derivative of this one. Okay, so now we have this term minus partial over partial x mu of partial L over partial mu phi. Okay, minus partial over partial x nu times partial L over partial times partial nu phi, right? And all of this is equal to 0. Okay, now just the next step is to put this take these derivatives and substitute the values in there. So if we go ahead and do that, what we are left with is mc over h bar whole squared phi minus 1 over 2 eta mu nu partial nu phi minus 1 over 2 eta mu nu partial mu phi is equal to 0, right? And of course we can then take this sum, and what we are left with is mc over h bar whole squared phi minus eta mu nu partial nu is times phi is equal to 0. Now if you recall, if you look at this equation, we have done a video on Klein-Gordon equation, and so this equation is essentially that. So we can write this equation as partial mu phi minus mc over h bar whole squared phi is equal to 0, and this equation is then the Klein-Gordon equation. Klein-Gordon equation, right? Okay, now in fact, even if you remember when I did this video on the Klein-Gordon equation, I said at the end of the video that this equation is only useful, or it is only used for the spin zero particles, right? And so we had this in this video we had this Lagrangian for spin zero particles, and from that Lagrangian the equation of motion that we derived is the Klein-Gordon equation, right? Okay, now let's talk about the spin 1 case, right? So spin 1. The spin 1 case they're also called vectors, right? And so we are going to talk about this one, that is a mu. Now for this we have the Lagrangian, that is this thing, 1 over 16 pi f mu nu plus 1 over 8 pi times mc over h bar squared a mu. And if you have done the Lagrangian part of the relativistic electrodynamics, the dynamics of relativistic fields, in that you must have encountered or visited this free Lagrangian, right? over here, again, from even in my previous videos, I have derived these f mu nus, right? And this is, or this was actually in fact simply equal to partial mu a nu minus partial nu a mu, right? And well, you can also, if you shift the indices, what you have is eta mu lambda times eta nu beta times f lambda beta, right? So if you compute this thing, you have essentially shifted the indices on your f. F is your electromagnetic field strength tensor. Right, okay. So again, our goal is to figure out the equation of motion for this case, and we do that simply by again computing this thing, partial L over partial A mu minus partial over partial x nu times partial L over partial nu A mu is equal to 0. Now you just have to actually compute these quantities, which should be a very good exercise for you. So if you go ahead and if you even look at if you look up at the Lagrangian that I just wrote, this thing partial L over partial A mu is simply equal to 1 over 4 pi times mc over h bar squared, the constants, and then this this quantity, right, which we had the derivative with respect to. Okay, so the next thing is then of course to compute partial L over partial times partial nu A mu, and this thing we have actually even computed in the video on the relativistic Lagrangians, right? I think it was on the relativistic Lagrangians, or it was in the relativistic electrodynamics, right? Or I don't know, I think I still have not made that video. Yeah, but anyway, you can compute this thing, right? And it turns out to be 1 over 4 pi times f mu nu. And it's not actually tough. It is actually very simple, right, if you go about it. So if you do that, then you put all of this back in your Euler-Lagrange equation. You get partial mu f mu nu minus the constants that are mc over h bar squared times A mu is equal to 0, right? And I'm sorry, times A nu is equal to 0, right? And this equation over here that we just got, this equation of motion, this is known as the Broca equation. And you might be able to recognize this equation if I say that we are talking about a massless fields, specifically, let me mention, the electromagnetic field, which is massless. And so all you have to do is put this m is equal to 0. And so if you do that, then you, let me get rid of this, yeah, you end up with simply partial mu f mu nu is equal to 0. And you know this equation, right? This equation gives you your Maxwell's equations. Well, actually half of the Maxwell's equations. Let me go ahead and write those down over here. This gives you your curl of B, which is equal to, minus partial E over T partially over partial t, so the time derivative of electric field, which is equal to 0, right? Usually you might have the current density over here, J, right? But if that's 0, so you could also have 0 over here. And the other equation is simply the gradient of electric field, which is equal to 0. You might again over here have the charge density, usually over here, right? And so these are the half Maxwell's equations, and these are the dynamical Maxwell's equations, right? And the other two, or the other half, you can that are the non-dynamical Maxwell's equations, you can get those from the electromagnetic geometry, right? And again, I talked a bit, very slightly in fact, about electromagnetic geometry in the video I made on the frameworks for doing physics. But these two non-dynamical equations, let me just write them down here, that are the curl of E is plus time derivative of magnetic field is equal to 0, and the divergence of magnetic field is equal to 0, right? These are the non-dynamical equations, and you get them from the electromagnetic geometry. You could also arrive at these two equations if you define a dual field strength tensor, which is something, sometimes it's written like this, right? So yeah, and I made a video on the relativistic electrodynamics in a tensor notation. In that video I derived all of these things, right? So in fact we even defined the electromagnetic strength tensor and the corresponding dual strength tensor, and we indeed derived all of these four Maxwell's equations from those, right? But then if you go back over here now, this equation is a more general one, where in case if we had a massive field, we would have this equation of motion. But it just turns out that the electromagnetic field is of course massless, and so this term just completely vanishes and we are left with this equation, right? So the Broca equation turns into this equation, right? Now finally, let's just talk about the spin half fields that, let me write it down over here, spin half, right? And so spin half fields, these are called the spinors, and these fields are represented with psi and psi bar, right? We have discussed psi and psi bar in the video on relativistic spinors, right? And the free Lagrangian for this spin half fields is it's a bit different, and it's written as h bar times c times psi bar gamma mu partial mu psi plus m c squared psi bar psi, right? Now note over here that psi and psi bar, we are going to treat both of these as independent degrees of freedom. This is for the reasons that we are going to discuss soon or in a later video, but I'm just going to say it over here that it turns out that the Dirac Lagrangian or the Dirac equation knows about something that we call the antiparticles, right? And so this is actually giving you a hint for the existence of antiparticles. And so if you think about it, let me stop over here and let me just talk a bit. If you think about it, this antiparticles, for someone who never heard about them, it might be very weird, right? And you might think, no, how could that be? That could not be true. And perhaps it's just mathematics, and so it could be wrong, right? Maybe it's wrong. Maybe there is some problem in the mathematics. It's just mathematics. How could it know about that? But this mathematical beauty of Dirac equation, the mathematics knows about these antiparticles. So these physical antiparticles which are actually there in existence. So once you carry out an experiment for detecting these antiparticles, you're surprised that yes, they are there. And this equation, even though we humans, we were neglecting or rejecting the idea for antiparticles, they are actually there, and the equation knows about these particles. So the mathematics knows about this. And so over here, I kind of understand the association that Dirac had with the beauty of mathematics, right? So Dirac's view was, if a theory is mathematically beautiful, then it has to be true. Whether experiments verify it or not, it just has to be true, right? Okay, so I got a lot of off topic over there. Let's come back to the topic. And first now, what we are going to do is we are going to solve the Euler-Lagrange equation, varying it with respect to psi bar, right? And like I said, that we are going to treat psi and psi bar as independent degrees of freedom. That's why we are first doing it with psi bar, and then we are going to do it with psi, right? So again, our goal is then to simply solve this equation, that is partial L over partial psi bar minus partial over partial x mu times partial L over partial times partial mu psi bar is equal to 0, right? Okay, and so if you solve this equation, I'm not going to do it now, right? It would be a good exercise for you to do it and then show that this thing is actually this gives you h bar gamma mu partial mu plus mc squared psi is equal to 0. And this equation, well, there is a very beautiful notation for this gamma mu, the contraction of gamma matrices, and this fourth derivative. It's used, I think it was first used by Feynman. It is d slash, right? So it's just the contraction of these two quantities is written as d slash. So we're going to use this notation and quickly rewrite this equation over here, and it becomes d slash psi plus mc over h bar times psi is equal to 0. And this equation over here is known as the Dirac equation. And so we have essentially derived the Dirac equation. Right. Now, remember that we only had varied right now with psi bar. We can also vary it now by varying with respect to psi, right? And again, we just have to solve this equation then, that is partial L over partial psi minus partial over partial x mu times partial L over partial times partial mu psi is equal to 0. Now, once you go ahead and you solve this equation, this part over here, it gives you mc squared psi bar minus partial mu times h bar c psi bar gamma mu is equal to 0, right? And this thing then you can simply write down with this d slash notation, d slash psi bar minus mc over h bar psi bar is equal to 0. And this equation over here, it also has a name, and it's the adjoint of the Dirac equation. So adjoint Dirac equation, right? And that is why you might see somewhere the Dirac equation written with this positive sign and somewhere with this negative sign, right? The differences of these psi, right? So in one of those we have psi and the other one we have psi bar. But the fact that we are getting these two equations and we have these psi and psi bar, this is already hinting us towards the fact that there are antiparticles in nature. Right, so I'm pretty much done with this lecture. In the next lecture, we are going to revisit all of these equation of motions, and we are going to interpret them, right? And we are going to understand what do they mean and the interpretation of these equations. Right, so yeah, that's it for this video. We will in the next video also see that we can satisfy all these equations that we have. In fact, the Dirac equation and the Broca equation, they are going to satisfy the Klein-Gordon equation, right? And in the next video we will see that why is that so, right? Why do they satisfy the Klein-Gordon equation? And if they do satisfy the Klein-Gordon equation, why do we have Dirac and Broca equation, and what do they exactly tell us, or what more do they tell us, right? Because if they're satisfying the Klein-Gordon equation, well, there is a reason for it, and it would be a good idea for you to think about it right now. But of course, if we are getting all these equations, they tell us something more as well. And so to understand that, we are going to do that in the next video in this particle physics series.